Now consider the case that we discussed at the beginning of the class. So the time rate of change of population is proportional to the population itself. Well, when we're solving an ordinary differential equation, sometimes we need to impose some initial conditions, some constraints at the beginning. So in that case, we have initial value problems. Initial value problems. What's the meaning of that? It means that suppose you have a differential equation, let the nth derivative of y with respect to x is equal to function f y and the nth minus 1 derivatives of y is given to us. And suppose we want our solution y of x satisfies some initial conditions. IC or initial condition. For example, in that case, when we find the formula for population, which is a solution for this differential equation, we want the population to have initial values. Well, in this case, the values for the solution and it's n minus 1 derivatives, which can be written this way: y at x sub 0 equals to y sub 0. The first derivative at x sub 0 is equal to y sub 1, and the nth minus 1 derivative at x sub 0 is equal to y sub n minus 1. These constants, these numbers, form the initial condition. So of course, we need to have an interval including x sub 0. There is an interval I that includes x sub 0. So when you're dealing with these types of differential equations, we call them initial value problems. Let us go over one example to feel more comfortable about initial value problems. In this example, we have the following. Show that phi of x equals to sine x minus cosine x is a solution of initial value problem, which is given to us as, well, the second derivative of y plus y equal to 0. This is our differential equation. And the conditions that we have is y at 0 must be -1. And the first derivative at 0 must be 1. So these are our initial conditions here. This is our differential equation. And these two are initial conditions. So in this case, the solution is given to us. We just need to check to see if this solution satisfies the differential equation and also the initial conditions. Let us check the solution. So in this case, as you can see, you need the second derivative of sine x minus cosine x. So your y is equal to sine x minus cosine x. Its first derivative is cosine x plus sine x, and the second derivative is negative sine x plus cosine x. Let us substitute. Well, the second derivative of y, negative sine x plus cosine x plus y, plus what is y? Sine x minus cosine x must be equal to 0. So this function is a solution of this differential equation. Well, this is obvious to see. These two are opposite to each other, also the same for cosine, and the sum is equal to 0. So left-hand side is equal to right-hand side. So far we know that this solution satisfies the differential equation. So the solution phi x equals to sine x minus cosine x, satisfying the second derivative of y plus y equal to 0. Now we need to check the initial conditions. Let us check the initial conditions. Very well. The first one says, hey, if you plug in 0 for your x, the y value must be -1. Let x be equal to 0. Phi of 0 is equal to sine 0 minus cosine 0. Well, this guy is 0 and this is 1. The outcome is -1. As you can see, as we plug in 0 into phi of x, our y value is -1. So we're good with the first condition. What about the second condition? The second condition says, hey, now if you plug in 0 into the first derivative of the solution, it must be equal to 1. Then you can say that, hey, this solution is the solution of this differential equation with these initial conditions. So let x be equal to 0 for phi prime of 0. Well, it's going to be cosine of 0 plus sine of 0, which obviously equals to 1. So this solution satisfies the initial conditions. It means that we have the solution for initial value problem. So phi of x equals to sine x minus cosine x is the solution of the initial value problem.